Well, here we are again, and I'm going to take you through the next stage in exploring these sine and cosine functions and what they look like when we graph them and how that relates to our unit circle work. So here's where we left off last lesson. This is the graph that we made on Desmos, which was super exciting to me, and maybe not so much to you, but that's all right. The other thing I can do is I can actually set it up as projector mode, so it makes it a bit thicker, which might be a bit nicer. Now I'm going to get rid of cosine. Let's just deal with sine. And I'm going to explore how we can change certain things about sine. So to do this, I'm going to have to start by zooming in a little bit. So I've now got it from -3 to 3, and the x scales also come in. And I'm going to have a look at how certain things change my my graph. So this is going to be a really important video because this relates back to the transformations we did when we did the algebra topic in Unit 1 of the course. So it'll be really important for you to understand and see the link between what I'm showing you here and what you see and did there. So here we go, let's have a look. Let's imagine that I want to just do a multiplier on the outside. So I'm just going to call it A because A is the standard. And who am I to deviate from the standard, hey? So I'm going to add a slider for A. And you can do this as well. The sliders on Desmos are really good. Now this is what happens as I change A, and it just automatically sets up an animation. I can always change these lengths, have A go from -5 to 5 if I want. And if I want it to move really differently or change, I can change the scale that it moves in as well. So I can change the step, maybe. You can normally change the step, but I can't. Oh, there it is. It's down the bottom there. So I can change it to 0.1 and it just moves nice and slow. Let's have a look at what happens if I change A, and I can animate this. So as A increases, it goes up, and then as it decreases, it kind of does the same thing. But I'm going to pause and talk about it a bit here. But I'm also going to, because it goes up to 5, let's just zoom out one level. So now we've got from -5 to 5. That's funny, you know, that I stopped at -5 to 5. But anyway, we'll get to that. So if I play this, it goes up to 5, and then it goes up to 5 again, even when it's negatives. But have a look what's happening. When A becomes negative, the whole graph is flipping. This bit is now high, A is negative, and this trough, this peak is now a trough, it's low, and now the trough becomes a peak again. So it's actually inverting itself as well, and the bits that were negative are now positive, and the bits that were positive are now negative. Definitely worth investing your time setting up a slider with A and just having a look at what happens. So there we go. So I'll stop A there, and I'm going to set A back as 1. 1's our standard for a multiplier. 1 is called the multiplicative identity, so it's where we're back to normal. Now let's set up another slider. This time we'll set up a +D. So this is one of our other standards, and again, who am I to change the standards? And I'm going to add a slider for D. I won't muck around with this. Oh yeah, I will, because it might get out of hand. So let's make it go from -4 up to 4, and the step can be 0.1 again. And we'll play this, and look what's happening now. So D has this this vertical transformation effect, which is amazing because that is what D did on the other functions. If you change your D value, it lifts the function up or drops it down, but it does a movement, a translation or a shift, and it does it vertically. So that's really cool. Again, brackets, I think is really cool. So I'm going to stop D now. I'm going to set D back as 1. So far we've got D and we've got A. And A was our vertical stretch, whereas D, oh, I hit 1 exactly then, did you see that? D was our vertical dilation. Sorry, it was our vertical translation, my apologies. Translation is a technical word for shift, and dilation is a technical word for stretch with A. But they're both vertical, and you'll notice that A is multiplied on the outside, D is added on the outside. I'm actually going to change D to 0 because that's our additive identity. So there we go, D is 0. Now I'm going to add in another one. What about inside the function? So I'm going to add in B, and just close the brackets there, make sure it doesn't do anything funny. So I'm doing an inside multiplier. Now, if I do this inside multiplier, have a look what happens when I change B. Oh, now it's the rate's changing, which makes it really hard to follow. So And I'm actually, the negative, all the negative does is does a flip over the y-axis, which for a sine graph is quite hard to notice. You'll see that the trough, the first thing on the positive axis is a trough. If I go into the negatives, it flips over, so it's now, the first thing on the positive axis is a peak, and now it's a trough. So that's all that happens. It flips from the positive x to the negative x. So I'm going to cut out the negatives. I'm going to make it go from 0 to 10, and up in 0.1s again, and let's play it again and see what happens. So it's actually compressing, now it's expanding. Now that's interesting because as b gets smaller, it expands. As b gets larger, it compresses, which is kind of opposite to what we would expect typically. So b is almost 5 then. If I go to 10, it's compressed it. If I go back to 2, it's expanded it. If I go to 1, it's like normal. If I go back a little bit more to say 0.5, it's stretched it out more. So it's done that expansion factor. Now our multiplicative identity is 1, so I'll just stick a 1 there again. So we're back to normal again. But our b has an effect on the horizontal, and it's a compression or stretch expansion factor. So again, it's a dilation. But it actually dilates opposite to what you'd expect. So if I change b to 2, it's actually compressed it by a half. You see here now, instead of going, if I have b as 1, I get one full repetition of the curve from 0 to 2 pi. Now when b is 2, I get one full repetition of the curve between 0 and pi. And I get two full repetitions at 2 pi. So 2 just increases the number of repetitions. So there's b equals 2. Let's change it back to 1 and explore the last one. And this one's, it's going to be a bit funny. So I'm going to show you the wrong way of doing it first. It's not the wrong way of doing it. It's just, it doesn't make things work as nice as we'd like. So here's my plus c. So we'll use the plus c. Now, if I do plus c like this and press play, it actually works exactly as you expect. Because remember, a and b were multiplied. A was multiplied on the outside, so it was vertical. B was multiplied on the inside, so it was horizontal. And they're both dilations. D is added on the outside, so it's a vertical translation. C is added on the inside, so it's a a horizontal translation. Let's have a look what happens. Oh, magic. So it is translating. Now, C does have this magical thing where it again, like B, works opposite what we expect. So you see how as it increases, as it goes up towards 10, it shifts backwards. You can see that movement. As I go back down to the negatives, it shifts forwards. So we counteract that by just making it bx minus c. Now that's good. And we get our shift. Fun. But it's still not perfect. Because I've got my b set as 1. We don't notice it. Let's say if I change my b to 0.5, which stretches it out a bit. There we go. So now it's double the compression factor. And I change my c now. Now, if I start at c equals 0, there, and change it to c equals 1, or actually in this case, let's change it to c equals pi. Now, we would expect this whole thing, that central point there, to shift out to pi, wouldn't we? So I'll change it to pi. It doesn't. It actually shifts out to 2 pi. Now that's a bit confusing and doesn't work the way we want it to work. So it does shift. It is a horizontal shift, but not the way we expect. So when we get to periodic functions, it's actually important now to recognize that we should put brackets around the x minus c. So I'll just work a bracket around here. Now you'll see what's happened is it shifts out to pi, as we expected. And if I play C now, you'll see we're back to, I've changed C as a slider, haven't I? There we go, sliders back. We're back to this moving as we'd expect. It goes up to 10, down to negative 10, etc., etc. So C is doing what we expect again because I've factorized it inside of my function. And that's actually really important for all functions, but in a lot of functions, you don't notice it. In this function you do. So if your b value is not 1, then you really need to have it factorized out for your c value to work the way you expect it to work. Massively important. Anyway, that's me 10 minutes just sitting here playing on Desmos talking about periodic functions. What I'm going to do now is probably leave this video as it is. and I'll make another one where I show you how we can put this into practice. Have fun.